Great. So welcome everyone. Welcome to the fourth day of 30-day challenge. And today we have semiconductor physics. So electronics basically is divided into 5 or 6 subtopics, and semiconductor physics is one of them. So today we will be completing the semiconductor physics. So I gave you these notes as a prerequisite read for that. And these notes, I can guarantee you, I can give you my assurance. If you know all the formulas, whichever is written in these notes, nothing, no question is going to come outside of this. You are not going to need even a single formula which is not in these notes but have ever came in exam so far. Okay, so let's begin. What is semiconductor material? So first of all, the semiconductor materials are those ones which who has a conductive properties between metals and insulators. This is some low class physics. We already know that who are conductive in between, who has conductivity between insulators and metals, they are basically known as semiconductor. But this is a very basic definition. How do we quantify these numbers? What is the actual properties of the semiconductor which makes it a semiconductor? Okay, so there are two kinds of semiconductors which are known as intrinsic and extrinsic. So first, let's have a very detailed discussion on what is intrinsic semiconductors. So in our elemental table, in our elements, we have group 14. And group 14 actually is the core of all the industry we have because it contains silicon, germanium, etc. These are the two materials which revolutionize the modern day world, and we are able to access everything because of these two materials, and more importantly, because of the silicon. Okay, so now what does group 14 elements have? So this is something group 14 elements. If you poke inside this group 14 element, you will see something like this. Okay, you have silicon, and every element has 4 valence electrons. So you can clearly see that if this is silicon, one here, one here, one here, one here, and there is another silicon, one here, one here, one here. So what will happen? The silicons will make bond with each other, which will be covalent bonds. Covalent bond means equal sharing of electrons. So this silicon and this silicon will combine together. Similarly, this silicon and lower silicon will combine. This and upper will combine. This and left will combine. And all these combinations you can see very nicely. This is what is inside the silicon element or material. But now what will happen? So can anyone tell me where we find silicon? How, if I want to find silicon, how do you find? Our phones have silicon. Our electronics, all the electronics gadget have silicon. How do you find the silicon in first place? Which ores? What is silicon? From where do we get all?
It can be extracted from silica.
Yeah, what is silica? Can you give more
Uh,
insight?
it's like
It's a
some sort of mitti,
sand.
mitti something, right?
Sand. It's
And
sand. Silicon oxide.
Sand,
SiO2.
sir.
okay,
SiO2, sand. Just go to the beach and pick up the sand. That's silica. Okay. So we the entire process, if you join the nanoscience department in Indian Institute of Science, they actually teach you that before even starting to make something on silicon, how do you get silicon at first place? And you will be surprised to know there is even not even a single company in India who is making silicon, pure silicon in India. So we have to import all of our silicon wafers from the China or from the USA, because it's a very technologically advanced process to come from sand to 99.9999% pure silicon, which we actually use. Okay, so we need 99.9999% pure silicon. There should be no impurity in it at all, even better than this. Okay, so what will happen if I heat this silicon up? So if I heat this silicon up, so bonds will break. So there will be a big breaking of bond between two of the silicon. So if the bond breaks, so what will happen? So when the bond breaks, so this is what will happen. So let's say this bond breaks. So if this bond breaks, you will get one free electron, because electron is getting free, and you will get one vacant position behind. Means this silicon wants to make the bond, but now the bond is broken. So whenever the bond breaks, two things happen. One, the electron gets free. So it is like that you have a silicon, and in the valence most electron, one of that electron went out. So one of the electron went out. So now you have a vacant position of electron in your valence band, and also one electron is outside. So two things produced whenever the bond break. One is free electron and one is hole. So in pure semiconductors, in intrinsic semiconductors, only thing that is producing charges is heat. Because of the heat, these bonds are breaking and we are getting two things. One is holes and one is electrons. Hole is nothing but the vacancy of it, that you have some position left where electron can come and sit. But in semiconductors, we usually consider the hole or assume that hole as a positive charge because it's easy to deal with. So you can just imagine that hole is nothing but a positive charged particle which has the charge E. Okay. Now, in intrinsic semiconductors, we define some of the parameters like, for example, Ne. What is Ne? It is number of free electrons per unit volume. And what is NH? Number of holes per unit volume. Can anyone guess the number? How much will this number approximately? How many free electrons are there per unit volume in any normal semiconductor you have in your hand? Okay. Anyone can guess the number?
10 to the power some 20, I think.
22. It's actually 10 to the power some 22, 23. It is a normal number per meter cube. Okay. So this is something we have. No, not around mole. It is 10 to the power 22, 23, something like this. So at room temperature, this many bonds are breaking. And you have this kind of concentrations. Or no, sorry, it is 10 to the power 40. No, this is fine. This number is fine, I guess. Okay. In intrinsic carrier, in intrinsic semiconductor, what is a major property? Because when the temperature came, bond breaks, so electron also produced, hole also produced. So whenever the bond will break, electron and hole will produce in equal numbers. Okay. So in intrinsic semiconductor, only thing that is producing charge concentrations is bond breaking. That is because of the temperature. That is the first thing we have to remember in our mind, that in intrinsic semiconductor, only temperature is giving us the charges because it is breaking the bonds. So whenever the bond breaks, equal number of electron and holes are produced. So charge carrier density of electrons and charge carrier density of holes is always same. And that if they are both are same, then we call it as Ni. What is Ni? Ni is known as intrinsic carrier density. Intrinsic carrier density. It basically means number of electrons per unit volume or number of holes per unit volume because their numbers are same. Okay. Now, coming from this to the law of mass action. So now there is a law of mass action which has a very sophisticated proof, and it is being respected a lot in semiconductor field. And this law says that number of electrons per unit volume. So I'm now from on small n means number of electrons per unit volume. So small n basic it itself means that we have divided by per unit volume. So all the discussion I'm doing, it is in per unit volume. So I will not repeat again and again per unit volume. Wherever you see small m, you have to think that I'm talking about per unit volume. So n is number of electrons per unit volume. P is number of holes per unit volume. If you multiply them, then you will get that n is also Ni, P is also Ni. So you will get Ni square. So you will say that what is so special about this? We already know that if n and p are equal and both of them are equal to Ni, then Np will be equals to Ni square. So what is so new about this, what you are telling? And why is it very important law? Not even in just intrinsic semiconductors, this law is valid for all semiconductors. You can use this formula even for extrinsic semiconductors where number of electrons and holes are not same. Even in that cases, this formula will always remain valid. Okay. That is the number one condition, and that is known as the law of mass action. If you choose to do MTech in semiconductors or PhD in that, you will be learning much more about this. Okay. Now the question comes that what is this number equals to? How do we calculate this Ni? What is the formula for this Ni? Very important formula. So whatever formulas I'm telling are very important. You have to memorize that. And in the end, I have also given the formula sheet to give you all the summary of all the formulas. So Ni is equals to N naught. N naught is some fixed number which depends upon the material. Okay, you are taking silicon or you are taking germanium or whatever material you are taking. Based on that, N naught is that number which depends upon the material into exponential minus Eg by 2 kBt. Now Eg is known as energy band gap, which I am coming up. What is energy band gap? And T is temperature. Looking at this formula, yes, it will be discussed in the end. Once I'm taking the brief summary of the lecture, and then in the end, I will be discussing problems. Okay. So exponential minus Eg by 2 kBt. Can you tell me by looking at the formula, if I increase the temperature, will my carrier density will increase or decrease?
It will increase exponentially.
It will increase exponentially because more you are hitting, more bonds will break, so more number of electrons and holes will come out. And you can even look from the formula as such that your with temperature your Ni is increasing, and increasing. This is the formula you have to keep in mind. Okay, very important. Now let's come to the band. What is band? So band is very important thing. First, understanding the band is very important. So you all know that in individual atoms, let's say for very basic example, n naught is a constant number which depends upon the material property, that which material it is. Or you can, okay, which material we are talking about here. Is it a silicon or what is it? Is it a germanium? Though that constant depends upon that material property. Okay. So what is individual atoms have? Individual atoms have discrete energy levels: 1 energy level, 2 energy level, 3 energy level. Similarly, this has 1 energy level, 2 energy level, 3 energy level. Ni is the number of intrinsic carrier density. Electron and holes are equal in number, and what is that equal number is equals to? That is equals to Ni. So N and P are equal, and they both are equals to Ni. Ni is some number I'm representing, so it is basically number of electrons per unit volume or number of holes per unit volume. Okay. Now, let's come to the band diagram. So band diagram basically says that you have two atoms. First atom has, let's say, how do we get the bands? So first atom has discrete energy levels, second has discrete energy levels. They both are existing in peacefully away from each other. Now someone decides, let's bring them together. So once I bring them together, the energy levels of this and energy levels of this will start interacting with each other. They will interact with each other. Similarly, the third atom will also come and they will also interact. Four atom will also come interact with. So all the atoms in a solid are interacting with each other, at least to the closest neighbors. Now, one atom is interacting with 3-4 atoms around it, resulting in formation of new energy. So before, what was happening, that you were possible that energy is available. You can either have energy E1, energy E2, energy E3, and so on. But once you combine them, once you combine the atoms, now you have something like this, that you get band. One band is upper band and one band is lower. And in each of the band, there are many energy levels, many closely spaced energy levels. In this also, many closely spaced. So let's say you have like this -2 electron volt to -3 electron volt. And then you have some free space. And then from here, or sorry, minus 10 to -9. And from here, you can say -3 to -2. So from here, what you can say, that now when the atoms combined, you can have any energy between 10 to 9. And then you can have no energy between 9 to 3. You can't have that energy. And then there is an upper band in which you have the energy from -3 to -2. So what happened is that your total energy level split into two parts. One part is below, one part is above. And in both the bands, there are many energy levels, many energy levels. This is same as the bands we form in the spectrums. You remember Lyman series, Balmer series, Paschen series. You might have also seen that. In Lyman series, you have many number of lines. Then there is a gap. Then we have Balmer series, many number of lines. Then we have the gap, again, many number of lines. So the same thing is happening. Then when atoms combine, the redistribution of energy happens. Because of that redistribution, we get bands. Okay. And so the one line definition of band is, it is the combination of many number of energy levels which are very closely spaced. The spacing between them is very small, very, very small. Okay. So that is the basic definition of band, and it happens because of the redistribution of the energy between the atoms. Okay. Now there are basically two types of band, and this is very important to listen. Okay. Because I'm not going to give you valence band, but what properties decide the semiconductors. So listen very carefully. Two bands. One is valence band, which is a lower energy band. This band is full of electrons. There are electrons. So consider it a room. So you have a room in which it is filled with people. So you will say it has so many electrons. So many electrons means so much electricity, but no. There are so many electrons, but there is no vacant space. So electrons are sitting, but there is no empty space where electrons can move. So in valence band, what is happening? Number of electrons is so large, but there is no vacant space. So electrons cannot move. So until unless electrons cannot move, they cannot have current or they cannot have conductivity. So remember one thing, electrons in valence band gives no conductivity. Electrons in valence band gives no conductivity. Okay. It is like that electron is bonded with the net. Until unless the electron is bonded with an atom, it is where it is in the valence band. It is in valence band. And once it is free, then it is not in valence. Okay. So electron bonded means it is in valence band. And until unless the electron is bonded, it cannot give you conductivity. And so in the valence band, what is happening here is that you have many electrons, but there is no free space to move around. So that is why electrons in the valence band gives you no conductivity. Okay. Now, however, holes in the valence band gives you a lot of conductivity. Now, let's say you do something. So this was a room full of people and you do something, you provide the heat and you kicked out some of the electrons. You say, okay, go from this room. So now in that room, there are holes produced. So wherever the electron leaves, it leaves behind some hole. So now your room has some vacant positions. Your room has some vacant positions. So now your electrons can move. So it gives you the conductivity. So motion means current and current means conductivity. So in valence band, who is giving you conductivity? Holes, empty spaces, because you are in a room which is already filled with so many people. So if you want to give conductivity in that room, you have to empty the places. So holes will actually give you the conductivity in the valence band. However, there is another band which is known as conduction band, which is above. It is a higher energy band and it contains the empty space. So it's a completely different room. So you had the one room which is filled with people and you had the another room which is completely empty. Now, do you think the vacant spaces in this can give you conductivity? No, it's already completely empty, but there is no one to move. The room is completely empty, but there is no one in that room which can move in this room. So current can be coming because so current can come. So holes in conduction band does not gives you conductivity. But let's say some of the electrons go to conduction. Then now these electrons can easily move in conduction. And then they will give the conductivity. So you have two bands, conduction band, valence. Who gives you conductivity and who does not give you conductivity? In valence band, electrons cannot give you conductivity because there are already many electrons. But there is no hole, empty space. So in valence band, electrons give you conductivity, but holes does not give you conductivity. In conduction band, what happens? Holes does not give you holes. Sorry, I written it. So in valence band, holes give you conductivity, and electron does not give you conductivity. However, if you go to the valence band, there are already all the space is empty. So holes cannot give you conductivity, but electrons will give you conductivity. But let's say in this vacant room, in this empty room, some of the electrons go and get into this room. Now they see the entire room is empty. So these electrons will jump here and there will be so much current. Okay. So valence band means electrons are bounded. Conduction band means electrons are free to move. So do you understand this concept? Do you understand this concept? It is
Yes, sir.
Yes, sir, it's clear.
It is
Yes, sir.
usually people think that okay, electrons and holes are giving us the conductivity in semiconductor. This is a wrong statement. You have to be very specific. Electrons in conduction band and holes in valence band are giving you conductivity. This is a proper statement. Okay, so with this statement clear, now between these two bands means between the electron being bounded and electron being free, there is some energy levels which are not possible. So either your electron can be bounded or your electron can be free. There is nothing in between which can happen. So that in between is known as energy gap. These are those energies which cannot be taken. So if electron is bonded, let's say, it has energy of minus 13.6. It's hydrogen atom, you remember. And if electron is free, it has zero energy. For example, I'm just taking a vague example here. So either electron will have this energy. So if it has this energy, it means it is in valence band. Or electron, if it gets free, it has conduction. In between, there is no energy possible. So this gap will be known as energy band gap. So this is a gap which actually decides that it actually tells you that these energies your electron or your atom can never have. Okay, this is a concept. So now let's look at the diagrams. So if for an insulator, if you see between the valence band and conduction band, there is a huge band gap. Means you need a very high energy to free your electron. So you have the electron. Insulator has so many electrons, but you need to free them. But you need a lot of energy to free them. That is why you don't have such energy available usually, and that is why your insulators do not have free electrons, and as a result, your insulator is a bad conductor of electricity. However, in semiconductors, this energy band gap is small. And this energy band gap is completely decided by the material we are using. Okay, so that is what I'm trying to make a point, that this band gap actually is decided by the type of material you are using. In insulator, this is very big. In semiconductors, it is small. So you can actually make your electrons free. You do not need so much energy to make your electron free. Okay, so for silicon, the band gap is 1.1 electron volt, and for germanium, it is 0.7 electron volt. No need to remember these numbers. Okay, just giving you for the reference purpose. And these numbers are at temperature 300. In conductors, what happens? Electrons are already free. So we have the overlapping bands. Means conduction band and valence band are overlapping with each other. There is almost no energy. Either no energy or almost very small energy band. So these are the three materials based on band. Okay. So these things I have already told you. Now coming to the point, does both electron and holes contribute to the electricity? Yes. And does they contribute to the electricity in the same direction or in opposite direction? So answer is they contribute to the electricity in the same direction. How? Let me make this point very simpler. So now you have a semiconductor material. Your bonds break, you have holes, and you have electrons. Now you apply the battery across this material. So holes can be considered as positive charges. I already told you, to make the simplification, you can assume holes as positive charges. Now you apply the battery. Now what will this positive terminal will do? It will repel this hole. So this hole is now moving in this direction. And what will this positive battery will do to electron? It will attract the electron. So now electron is moving in this direction. So positive charge is moving in this direction and negative charge is moving in this direction. So you know from the basic electricity, in whatever direction your hole is moving or your positive charge is moving, your current will also be in the same direction. And in whatever direction your negative charge is moving, your current will be in the opposite direction. I hope everyone knows that if the positive charge is moving to right, then current is also to the right. But if the negative charge is moving to the left, then the current is to the right. So current is always opposite to the motion of negative charges. So you can clearly see that current is in the same direction for both of them, for even for holes as well, for electrons as well. So current, because of both, will go in the same direction, is in the same direction. So both of them are contributing towards the conductivity of the semiconductor. It's not just any one, like one of them, but both of them are contributing to the conductivity. Okay, so in semiconductor, what we learned? So we learned that electron and holes both contribute to the conductivity. Electrons in conduction band and holes in valence band. Okay, so am I clear till here? Any doubts? Everyone find
So will
Sir,
the
I
mass
have
of the holes or electron affect it?
Yes,
Because
I am coming to this. I am coming to this. That is the mass difference per se. Yes.
I have another question, sir.
Yeah.
Earlier you mentioned that whenever a valence bond breaks, it creates one pair of electron and hole, right?
Yeah.
In making of a valence bond, there are two electrons taking the part,
Yeah.
right? So what happens to the other electron? Why doesn't two pairs of holes and electrons are found?
Okay. So so it is like half. Contribution is half. Okay. So a very good question. So this question also pondered me a long back. So if silicon, okay, and if this bond has two electrons, okay, now if this bond breaks, what do I mean by that? This bond is breaking. This bond breaks. So silicon bond breaks. Okay. Now ideally, what should happen? That this silicon will keep its own electron, and this silicon will keep his own electron. So what is happening here? So see, this silicon kept his electron, this silicon kept his electron. So what happened? Right? What actually happened? So actually, in ideal picture, this is not how the things are working. That you have. So now what is happening is bond ban gaya. So now this is not like that. These electrons are localized here. These electrons sometimes are coming here, sometimes they're going here. So electrons are inside moving little bit here. So bond to bond electrons are moving. This is if you went inside the picture of silicon, what is happening once the bonds are formed? Now all the electrons which are bonded are in some sort of band, and all the electrons which are free are in other form. So you cannot localize each and every electron that, okay, this electron is here, this electron is here, this electron is here. No. Once whatever electrons are bonded, you treat all of them equally. And whenever the bond breaks, means you're bringing one electron from valence band to the conduction. One of them to the valence to the conduction. How one bond contributes half to this and half to this. So if one bond is breaking, then half plus half will give you 1, not 2. It is actually half of the contribution is to this and half of the contribution. So one bond breaking has half plus half, one electron and 1. You cannot say 2, 2. Cannot say 2, 2. And you can do this calculation that how do I say silicon. Okay. So silicon, and now, so it had 4 electrons. It had 4 electrons. Now, if I break this, so these 2 electrons are equally shared between this and this. So 2 electrons are being equally shared. 8 electrons now. It has 8 electrons now. It has. So now I just bring the 1 electron out. So you can ideally say that, okay, now they combined have the 7 electrons still, right? They still have combined 7 electrons. So what I picture, imagine my silicon as, I do not imagine this image, I imagine my silicon as now energy has been redistributed, and then like all the electrons are sitting somewhere in one valence band and free spaces are in condition. I will talk about this much more in the end as well. Okay. I just want to complete first. Any other doubt? Any other thing?
Excuse me, sir.
Yeah.
Sir, are intrinsic semiconductors without any kind of defect? Like we have read about defects in solid. So
No,
is there any
they
kind
are,
of defect in?
we make them complete perfect, very much perfect. Their defects come very quickly defects come. But that is why all the nanotechnology development is done in a clean room. They can come very fast, very fast. Okay, so anything can diffuse, but all the defects are restricted to the surface mostly. So if you have a wafer, let's say CD, you all have seen CD. So CD, so your silicon wafers comes in the shape of CD. Now CD has some thickness. When whatever defects are coming because of the environment or something, all of them mostly are to the surface. So when you are using this CD, you will clean the top surface. You will completely remove the top surface, and now the whatever silicon is left in your hand is pure, is defectless. That is the entire engineering, how to make this defectless silicons. Okay, but ideally if you are making it in a very random environment, then it will have a lot of defects. Very easy to get defects. When we find it in the nature, it is full of defects, and we completely restructure that silicon and bring a very pure silicon in our hand. Okay, you should look at this. Okay, so look at the video of ignot formation. So go to the YouTube and search how the ignots are. Okay, it's a very cool video where they show you how the silicon wafers are made. Okay, good. Okay, let's move to the next part. What is drift velocity? So you have a material. Now look at the material at the average basis. Now don't focus on one atom. Now for this topic, now we are going to look at the entire semiconductor at once. So now you have some sort of material, and let's say in that material, so some of the electrons are free. So some bond break, electron got free, and now electron is in the environment, and now electron is completely free to move, and electron is moving. When the electron is moving, it will go and move, and it will hit the other atom, and it will have the collision. So its direction will change. Then it will see another atom and it will again hit, and collision, its direction will again change. So in the path, electron is hitting the atoms again and again. So if it is hitting the atoms again and again, and if you have applied no electric field, so let's say you have applied no electric field, so you can see how bad your motion is. So your electron went here, then come here, 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 here. Randomly it is moving here and there. So you can see that electron is not going from one position to another. It is just randomly colliding in this region only. So because of the collisions, it is not able to pass through this region and actually go from this position to this position. But now let's say I apply the electrons. In this side I apply negative, and in this side I apply positive. So now this electron is also experiencing one pushing force in this direction. Electrons are being pushed in this direction. They are still colliding. You can clearly see the collisions are still there. But now overall they have some drift in one direction. They are also drifting. So that is a difference between moving and drifting. If I say they are moving from one position to another, then you assume that your electron starts from here and it is going in this direction. But drifting word means that they are not actually going from here to here straight line. They are colliding, but also overall motion is that they are actually able to move from one position to another. So because of the random motion of electrons, if you apply no electric field, they will just keep on colliding here and there. And they will not go from one position to another. But let's say you apply the electric field, then they will go from one position to another. And the speed with which they are going from one position to another position is known as the drift velocity. And it is a very small velocity. It's not very large. Very, very small velocity. The drift velocities are very small in number. It's almost centimeter per second or something, even lesser than that. Okay. So electrons are moving, and with what velocity they are going from one position to another, overall is known as the drift velocity. Okay. Is it clear, everyone? What is the meaning of drift? Whenever someone asks you the meaning of drift, just show him the two diagrams and he will give you full marks. Not just marks, he will be impressed in the interview. Okay. So these two diagrams actually show you that what is the meaning of drift. Okay. So drift is a combination of two things: electric field plus collisions. Okay. So then you get the drift. Clear, everyone? Yes, no?
Yes.
Okay.
Yes, sir.
Then comes the next point. If electrons are moving, what will come? Current will. Okay. So I'm telling you everything in terms of current, and in the end, when my final formulas are ready, I will also include holes in it. Okay. So currently I'm doing all the mathematics for electrons, and then in semiconductors, both electrons and holes are contributing. So I will add the contribution of holes as well in the end. Now, current density. Usually we are never interested in current. We are mostly interested in current density. What is current density? So let's say you have the wire, which is cylindrical wire, and the total current is flowing in this I. And the cross-sectional area is given as A. So the current density is total current divided by cross-sectional area, which is I by A. Okay, I by A. So basically, how much current density is there, that is much more important in conductors, because that will decide that how strong your current is. Okay, you might have a very large conductor but very small, then it is not important. Okay, so current density is current per unit cross-sectional area. And the formula for current in the conductors is given as in N, which is number density, number of charges per unit volume, E, charge on one electron, area, which is cross-sectional area, and VD, which is drift velocity. And what is J? J is current per unit area. So current per unit area will give you, area will get divided, NEV. Very important formula. You have to remember this. So do we need the proof of this? No, we do not, but I will give you the proof just for your simplicity purpose. A very quick proof which I have is that, let's say your electrons are moving with the drift velocity, VD. So you take some area of the electrons. So let's say I am taking this many electrons. How many electrons? Whatever electrons are there in my area A. So I am taking this much area of my electrons. So I have electrons here and there, but I am taking only this section. So I am seeing that whatever electrons are inside this section, and all of these electrons are moving with velocity Vd, drift velocity Vd. So let's say these electrons moved with velocity Vd. How much they will move in time t? So displacement is given by speed into time, and speed is Vd and t is t. So this length will be equal to Vd. So your electrons move. So the electrons moved by amount Vd into t. This is the length. how many total number of electrons will be there inside this volume. So you know number of electrons per unit volume is given by n. So if I multiply by the volume, I will get what is the total number of electrons inside this cylinder. That will be given by n. Okay. What will be the total charge? So this is the total number of electrons. So I have to multiply with E to get my total charge. So I multiplied by E. Charge on one electron is E. I have total this number of electrons. So my total charge will be NV into E. So total charge is NVE. Okay. Now, what is volume? What is this volume? This volume is area. What is a volume? Volume is area into length. Area it is already given, and length I have already calculated, which is VD into T. So the charge comes out to be NAVDTA. What is current? Current is nothing but charge per unit time. So if you divide by time, you will get your formula for current as NEA. So it's a very basic derivation, standard derivation. Usually you should know these derivations, because in any interview they can just give you the pen and they will throw you to the blackboard and they will say derive this. Okay, so you should be very good in this deriving this random formulas from here and there. But you can derive the formula only when back of the mind you should know that where I have to reach. My current formula is what? It is NEA. Okay, you can go through this derivation again once. Okay, now mobility. So entire semiconductor industry is running behind one thing: how to improve mobility of the material, how to improve mobility of the material, how to improve mobility. Better the mobility, better the device you have. My entire research was on how I can improve my mobility of the device. Okay, so what is this mobility? So why the electrons are drifting? Because I applied the electric field. What I am interested in, that if I apply my electric field, how much they will drift. So drift velocity per unit electric field will give me the mobility. If the material is very good, so if I apply the small electric field, the drift will be very fast. But if the material is not very good, the collisions are more. Okay, what will happen? If the collisions are very more, then what will happen? I apply a very strong electric field, but still the drift is very slow. So mobility should be more. Small electric field, even if I apply small electric field, drift should be very fast. So drift velocity per unit electric field gives you the mobility. This is what you are getting. You are getting drift velocity. This is what you are applying. You are applying electric. So what you are getting divided by what you applied gives you the mobility. Okay. In research, what is happening here is even the ballistic motions are possible. What is ballistic motions? So we are producing the channels. So basically, let's say this is your any electrical instrument, very small. So it's in the size of 2 nanometers. This is your transistor. So this is how the transistors are made at the low scale, nanoscale level. The size of one transistor at nanoscale is 2 nanometer, 5 nanometer, 10 nanometer. Okay. So you are making the transistor at, let's say, size of 10 nanometers. Okay. Now, what is happening here is we are achieving such things that your electron starts from here. Sorry. Electron starts from here and it faces no collision and it directly goes from here. No collision. You can imagine electron going from one position to another without any collision. Direct. This is known as ballistic motions in transistor. And people are researching on it. We are achieving the ballistic motions in the labs. Okay. And let's say we make our instrument based on this ballistic motion transistors. You can imagine what will happen. This is based on the two-dimensional material. We are using two-dimensional materials to achieve this. Okay. This what I have showed you is nothing but two-dimensional atoms like graphene or HBN, right? This is what we are achieving right now. So if there is no collision in the entire path, so you apply the electric field, electron goes shoot from one to another place, no resistance at all. Resistance comes because of the collision. And if you avoid any collision, you can imagine how much energy you are going to save. That is the level of research which is happening. That is why government is putting so much money in the semiconductor industry. And these things are not something I'm just saying. This is happening in labs. And in 10, 20, 30 years, you will see this in the devices, actual devices. Okay. Okay.
सर
Yeah.
सर ये जो बैलिस्टिक मटेरियल जो भी बताया ये इसमें उसका कारण क्या है मैं कि इतना स्मूथ मूविंग का और विदाउट एनी कोलिजन ऑफ इलेक्ट्रॉन
So we made the size very small, 10 nanometers. You need a very precise. So within 10 nanometers, you are shrinked your transistor to 10 nanometers. Okay. And you are making it defect free. So you are covering this material from bottom as well as from the top. Now you have to imagine this. I gave you one sheet, just one sheet, which is of the size of 10 nanometer. What is 10 nanometer? Just 100 electrons, 100 atoms. That's it. From here to here, you only have 100 atoms. And this is even less than that. That is just 2 nanometers. So here, from here to here, you have only 20 atoms. So I give you this tiny sheet. You have to pick this sheet, put something below this, put something above this. So this sheet is completely saved from surrounding. And now when the electrons will flow in this, no one is there to stop it. Okay. So that is kind of precise engineering we have done to make it very small and completely insulated from everything. Okay. Because these are the atoms. There is nothing below, nothing above. Only one layer of atoms. Electron is flowing in only one layer of atoms. No atoms are below this, no atoms are above this. In our 3D electronics, what happens? We have atoms, many layers are above it, many layers are below it. So electron can even collide with above layers, below layers, any layers it can collide. But now we have only one layer of atoms. Probability of collision is 1 in million. Okay, electron is so small, and you are only talking about 2000 atoms. That's it. From here to here, you only have 2000 electrons. So if you only have 2000 electrons and electron is 2000 atoms, and electron is so small, you can calculate the probability. Probability of collision will be 1 in millions, right? That is why we can achieve this ballistic transport. Okay.
Thank you so much, sir.
Okay. Now let's move to the next thing. Ohm's law in microscope, macroscopic form. Now there are two things: microscopic, macroscopic. Whenever the properties does not depend upon the size of the conductor. Now, voltage does depend upon the size of it. How? Because the formula you remember, voltage equals to electric field into distance. Voltage equals to electric field into distance. This is a formula, very important formula from electrostatics. You should know that. So you can clearly see if I increase the distance or the length of the conductor, my voltage will also increase. So you can even imagine that if you have a longer conductor, then the voltage drop across this will be more. And if you have a smaller conductor, voltage drop across it will be less. Okay. So voltage depends upon the size of it, but electric field does not depend upon the size. You remember between the two plates, electric field is sigma by epsilon 1. It does not depend upon what size you have. Okay. Electric field is not depending upon the size of the conductor, but voltage depends upon the size. Why? Because voltage is nothing but electric field into D. So if D increases, voltage increases. But electric field remains. Okay. Also, current also depends upon the size. R also depends upon the size, that what is the conductor's size as such. Okay. But if you talk about microscopic form, I can convert this into the law which does not depend upon the size of the conductor. Some people say microscopic. Some people are confused with macroscopic and microscopic word. Macro they think is large and micro they think is small. No, macro means which depends upon the size and micro means which does not depend upon the size. Now my microscopic Ohm's law says that J equals to sigma E. J is what? Current per unit area. Current per unit area. You remember J formula NEVD. N does not depend upon the size because it is number per unit volume. E does not depend upon the size. VD also does not depend upon the size. So your J does not depend upon the size. Similarly, sigma. Sigma also does not depend upon the size of it. Okay. Drift velocity also does not. So electric field also does not depend upon the size. So, and no term in this law depends upon the size of it. That is why it is known as the microscopic form of Ohm's law. How we come from here to here? Very simple. You use this formula V equals to IR, and voltage I just told you is what? Electric field into length, EL. Current is what? J into A, because J is what? Current per unit area. So I will be what? J into area. And what is resistance? So I hope from the basic electronics, you know that resistance is given by rho L by A, where rho is the resistivity, L is the length, and A is the area. So if I put all of these things, my area will cancel out, and my length will cancel out. I will get E equals to rho J. Rho is the resistivity, and the units of resistivity is ohms meter. Okay. And if I bring this rho on other side, I will get 1 by rho E equals to J. And 1 by rho is nothing but conductivity. So conductivity is known as 1 by resistivity. So its units are per ohm per meter. Okay, or we also call these units as SIM. So this is how you go from this law to this law. Okay, so do you understand about the Ohm's law? Very important for J equals to sigma E, again very important. And one more important formula which I am going to give you is, what is conductivity? Basically, I told you that it tells that how fast, how much your material can conduct. Units also I told you. Now let's derive the formula for conductivity. What is the formula for conductivity? Okay. So you know that what is J? J is, I derived already the formula. J equals to NEV. And NEI remain as such. And then I put it in the form of mobility. What is mobility? Mobility is drift velocity per unit electric field. So what will be my VD? VD will be nothing but mobility into electric field. So I put my value of VD here as nu E. So my J is equals to NE mu into electric field. Okay. Now I will compare it with the Ohm's law, which is nothing but J equals to sigma E. So my sigma will come out to be NE mu. So this thing is, entire thing is sigma. So my conductivity is Ne mu, where N is the charge density, E is the electron, charge on electron, and mu is the mobility of the material. Electron mobility. Okay. Now I did all the calculations. Now it is time that I also add the contribution of holes. Because in semiconductor, both of them are contributing, electrons as well and holes as well. So for electrons, what will be the situation? Ne, charge carrier density of electrons, into E, charge on electron, nu E, which is mobility of electrons, plus NH, charge carrier density of holes, E into nu H, which means the mobility of the holes. Okay, so this will be your sigma in this situation. Okay, so this will be your sigma, and your sigma will come out to be Ne nu E plus NH nu H into E. So you are contributing, you are adding the contribution because of the both of the situations. Okay, so one above and one below. This formula for sigma, I cannot tell you how important it is. All the questions are based on this formula. Sigma equals to Ne mu E plus NH mu H into E. Okay, and in the last terms, I will say that relaxation term. Relaxation time. What is relaxation time? Relaxation time basically decides that now your electrons are colliding here and there, here and there. If your electrons are colliding here and there, then between two collisions, there will be some average time. Let's say first collision happened, and then after 1 microsecond, second collision. And then after 3 microsecond again, one collision happened, after 10 microsecond again, and then after 0.1 microsecond again. So there will be some average of all these times. So what is an average time between one collision and another? And the formula for your relaxation time, so the symbol of relaxation time is tau, and the formula for relaxation time is this, that conductivity equals to Ne square tau by M. M is the mass of electrons. Okay. So this is the situation. Any doubt till here? Okay.
Sir, how
Any
is it
doubt?
derived, the formula?
You don't need the derivation.
Okay.
You can derive it, but no need as such. You have to go to the mic calculation. Not much important. Any doubts, anyone? Is it clear, everyone, till here? Read these notes very carefully. Okay. Please tell me, is it clear, everyone, till here? Can I move forward?
Yes, sir.
Okay. Then let's talk about the variation of conductivity with temperature. And you guys know it. What happens to the conductivity if I increase the temperature in semiconductors? Let's say I have semiconductor and I'm increasing its temperature. What will happen to its conductivity?
So it will increase.
It will increase.
Increases.
Any MSc, BSc student knows that. Why? Because see, in conductors, what is happening? There are already many free electrons. We don't need any more free electrons. So once you increase the conductors, there are vibrations start happening. Atom starts to vibrate. So number of collisions also increases. So if number of collisions are increasing, the resistance will increase. So in conductors, it is very basic theory that you increase temperature, your vibrations will increase, and as a result, collisions will increase. As a result, resistance will increase, and your conductivity is decreasing. So for conductors, you can clearly see that your conductivity is decreasing with temperature. But now in semiconductors, what happens? All of that is happening. I am not saying that vibrations are not increasing in semiconductors, but in semiconductor, one more thing is happening. As you increase the temperature, more and more bonds are breaking. and you are getting the bulk of free electrons. You don't have much free electrons to start with. But as you keep on increasing the temperature, your bonds are breaking in a huge number, and you are producing a lot more free electrons, and these free electrons will move in an empty room. Which empty room? Conduction band. They will move in an empty room, and as a result, they will give you the very high conductivity, very high conductivity. Okay, and that will actually. So what will happen as you keep on increasing temperature? Number of electrons and holes keep on increasing. As a result, you know the formula of conductivity: Ne nu plus Ne nu E plus NHE nu H. So if N starts to increase and NH also starts to increase, what will happen? Your conductivity will also start to increase. So that is what happens in case of semiconductors. So conductivity increases with temperature in case of semiconductors. Okay. What do you say? Should we stop here for today and start from here, or should I keep on going? It's completely your call. I can go on. Is it okay? You can take more information.
Yes, sir.
Okay. So let's
Yes,
keep on going. Yeah, let's keep on going. So now we covered everything in depth for intrinsic. Now it is time we go on for extrinsic semiconductors. We have some material. We call it as intrinsic semiconductor. We have silicon. Now it is time to dope this. Any idea how do you dope? Any idea? How do you do the doping? So you have one, let's say I give you silicon and I say, okay, dope it with some other. So put some other atoms in. So if it is silicon, add boron in it. How do you add boron in this? Any guess?
Something diffusion we do, sir. Diffusion.
Fusion.
Diffusion we do. What do
Heating.
we? No, we cannot heat. We have to put boron inside. How do we put boron inside this silicon?
Sir, we can make that solid silicon intrinsic material in liquid form, and we will also take the liquid form of the boron and then put the boron on one side of that solid
cannot,
intrinsic.
No, not at all. You cannot melt your silicon. If you melt your silicon,
Oh, sir. Thank you,
you
sir.
cannot melt. You cannot even touch the silicon. Melt though is very different situation. You can heat your silicon, but if it starts melting, then melting point of silicon is I think is beyond 2000 Kelvin. Okay, you cannot melt. Even if you melt, everything is broken. Your silicon is now not pure. So what we do is ion implantation. Ion in implantation. What we do is we make boron as ions. Remove the electron of boron, so boron gets positively charged, and now use a high electric field. So boron is at very high speed, and it goes and hits silicon. So now it enters the silicon. This is known as ion implantation. There are different ways of doing the what you can say doping. Second way is, so now you have a very balanced silicon. What do? You remove the top layer of silicon. Now the top layer of silicon is removed, so it is now ready to take something from the environment because you removed the top layer. Now all the bonds of the top layer are broken, and now they're ready to take something from the above. Now you pass the boron gas. So the surface of this will attract the boron, and this boron will go and attach, and slowly this boron will find its way and reach inside the silicon. So there are different ways. Yeah.
Excuse me, sir. I just have one question. Like,
Yeah.
The layer is already 10 to the power of -9 or 10 meters thin.
No. Thickness is in millimeters.
Yes, sir. It's in millimeters, sir.
Yeah,
Okay.
In our modern electronics, which we are using in our devices, the thickness is in millimeters.
I just wanted to know. Yes, sir.
It is
How
of the
do
same.
they? Yes, sir.
It is of the same size of our CD. CDs we have, right? CDs, it is of the same size. Okay.
Yes, sir. I was just curious.
Yeah,
How
ballistic
they remove
transport I
the
was
top.
telling you, that is very small. But in this
Okay.
case, it is not small. Yeah.
Okay, sir.
Okay.
I was just curious how they remove the top layer. So
Yeah,
just
it's a millimeter. You can easily remove it with HF2. So you have very toxic chemicals. Dip it in HF2, the top layer will be removed.
okay. Thank you, sir.
Okay. Or you can do etching, and there is an entire process, manufacturing process. Okay. Now, there are two kinds of extrinsic semiconductors. One is N-type. So you have group 14 elements. Now you have group 15 elements. Group 14 elements have 4 electrons in their valence. Group 15 has 5 electrons in their valence. What are group 15 elements? Phosphorus, arsenic, antimony, etc. These are known as pentavalent impurities. Why? Because in their valence orbital there are 5 electrons. Now you have group 14, group 15, combine them together. So now not just exactly combining, what we are doing is we are putting some of the phosphorus inside. So phosphorus will go inside, it will remove the silicon from here, and it will go and sit at the position of the silicon. Now, this phosphorus had 4 electrons. It made the bond with this, it made the bond with this, it made the bond with this, and it made the bond with this. But one of the electrons still has not been made any bond. So now this electron is a free electron. So now you are getting more free electrons. Initially, why were you getting free electrons? Because bonds were breaking. Now you have 2 methods to go get the free electrons. Number 1 method, bonds are breaking. Okay. So you are getting free electrons, you are also getting holes. Second method, why the free electrons came? Because you doped. So each dopant atom gives you 1 free electron. Because when the phosphorus will go and sit here, it will make the 4 bonds with silicon, but its 5th electron will not make bond with anyone. So this electron will actually give rise to 1 extra free electron. So now electrons are coming from 2 ways. One because of doping and one because of bond breaking. But what about holes? Holes are coming only because of one thing, that is bond breaking. So only because of bond breaking, your holes are coming. So you can clearly see that number of electrons will become much larger than number of holes. Because electrons are coming bond breaking as well as doping. But holes are coming only because of bond breaking. So now you can clearly see number of electrons will be much larger than number of holes. So in N-type semiconductor, your number of electrons is much greater than number of holes, and number of electrons is in majority. So electrons are known as majority charge carriers, while the holes are known as minority charge carriers. Okay. Now, let's say, because of the bond breaking, so let's say 10 bonds break. 10 bonds break. So 10 bond breaks, so you get 10 electrons, 10 holes. Now you put the 100 dopants. 100 dopants. So let's say you put 100 phosphorus atoms. So once you put 100 phosphorus, or let's say you put 10 is per 6 phosphorus atoms. You put 10 is per 6 phosphorus atoms. So large. 10 lakh phosphorus atoms. Each phosphorus atom will give you 1 free electron each. So now what is your total number of electrons? 10 is per 6 plus 10. Can I ignore this 10 with respect to 10 is per 6? Obviously. I can ignore this 10 with respect to 10 is power 6. So electrons coming because of the doping is much more than electrons which are coming because of bond breaking. So what we say, that your total number of electrons are almost equal to the number of dopant atoms that you have added. Do you all understand this point? That your number of electrons will simply be equal to how many dopant atoms you have added, because each dopant atom is giving you 1 electron. Okay. Do you all agree with me? This is very important.
Yes.
Okay. So number of electrons is basically equals to number of dopants you have. Okay. So because, okay. Now next step. What will be the number of holes? So now the law of mass action will come. Number of electrons into number of holes equals to Ni square. Number of electrons you already know is Nd. Number of holes is P equals to Ni square. So number of holes will be equals to Ni square by Nd. So whenever someone asks you in N-type semiconductor, what are the number of electrons? You will use this one. And let's say someone asks you what is the number of holes in your N-type semiconductor, you will use this one. Very important to focus. Okay. Now let's move to the next type of semiconductor, which is P-type. What you do in now, you have the group 14 elements, you have the group 13 elements. What are group 13? Boron, aluminium, gallium, indium. Okay. They are known as trivalent impurities. Why? Because they only have 3 electrons in the valence. Only 3. So now what will happen? The same way you will put boron inside. You will put boron inside. So what will happen? What will happen? So you will go some places, silicon will replaced by boron. Now boron only has 3 electrons. Boron only has 3 electrons. So what will happen? The fourth bond has not formed. The fourth bond has not formed. So it has given you the hole, vacancy of electron. Means if this boron had the electron, then this silicon would have made the bond. But since this boron does not have the electron, that is why the bond is not being made. That is why there is a vacancy of electron or the absence of electron. No bond means that there is no electron here. That is why the bond is not being able to made. There is a missing electron. Missing electron basically means hole. So now holes are coming because of the two things. Can you guess it? Number one is temperature. Bond is breaking, holes is coming. And second is because of the doping. So the amount of doping you will do too. So each dopant atom will give you one hole. Okay. So in this case, holes are being generated because of two methods. But electron, they are coming only because of one, which is bond breaking. So you can easily guess that number of holes will be much, much larger than number of electrons. Okay. So P is much, much greater than 10. So what will be this P will be equals to? Now P will be equals to doping. Whatever doping you did, let's say you put 10 raised to power 6 dopants. So your P will also be almost equals to n raised to power D. And how you find the number of electrons? Number of electrons you found using the formula Np equals to Ni square. So N will be equals to Ni square by N by P. And P you have already found is Ni square by N. So in P-type semiconductor, if someone asks you what is the number of holes, you say Nd. But let's say someone asks you what is the number of electrons, then you say Ni square by N. Clear till here, please, anyone? Fine. You can open these notes with you if you want the reading. Is it everyone okay till here?
सर
Yeah.
सर एक प्रश्न था ये जो ND is approximately to number of holes or number of electrons. Then सर यहाँ पे जो हम डोपिंग कर रहे हैं whatever we doped in माने कि pentavalent and trivalent impurity, तो सर ये जो डोपिंग है ये तो 1:2 माने कि बहुत कम हम करते हैं, ज्यादा तो नहीं करते, तो ये इतने मेजोरिटी माने कि 10 की पावर 6 के रेंज में कैसे हम डोप कर पा रहे हैं, वो थोड़ा समझना है.
We do doping a lot. So we have 10 raised to power 22 atoms intrinsically. Okay? And we are doping 10 raised to power 6. Then the ratio is coming as 10 raised to power 6. You see, there is one atom per million. This is what you are saying, that we dope very less. Dope very less means for 1 lakh silicon atoms, we have just one boron. So you have one atom per million. But in reality, if you look at the situation, you have 10 raised to power 22 silicons, 10 raised to power 22 silicons, and you have 10 raised to power 16 dopants. Then if you do the ratio, then you will get 10 raised to power 6. Then you are saying that, okay, you have just one boron in 10 lakh silicons. But in reality, you have 10 raised to power 16 dopant inside it, right? But your number of silicons are much greater. They are in 10 raised to power 22. But your dopants are also not less. They are in 10 raised to power 16. Okay. But their ratio is very small. If you take their ratio, it is only 10 raised to power 6. It means one boron in 10 raised to power 6 number of silicons. Right? That is the meaning of small doping. Even after small doping, you still have how many number of electrons or how many number of holes because of the doping? 10 raised to power 16. Can you guess the number? How large it is? Okay.
Thank you so much, sir.
Okay. Anything else? Everyone clear till here? Okay. Now let's talk about the band diagrams and Fermi levels. So if you have intrinsic semiconductor, you have conduction band, you have valence band, and between them you have a energy band gap. So what will happen if you heat it up? The electron will jump from valence band to conduction band. So as a result, hole will be generated in valence band and electron will be generated in the conduction. This electron is a free electron. This will also give conductivity. This will also give conductivity. In this case, the Fermi energy level. Fermi energy level is something, the physical quantity we define as, it decides that at which energy level your entire, so it has many definitions. And I can guarantee you the definition you are aware about Fermi energy is from statistical mechanics. So let's come out of that definition. First of all, let's forget that whatever you know about Fermi energy and listen to me that what I'm going to tell you about Fermi energy. Fermi energy tells you in electronics that at what energy level on average your system is at. So let's say your Fermi energy level is 2 electrons, or you can think that you have a system and it is like a bucket and you have water in it. Up to whatever level your water is filled, that is known as Fermi energy in electronics. You can do this assumption, nothing will break down. If you are talking about electronics term, think like you have a material and you have a bucket of water, and up to whatever level your water is filled up, that level is known as Fermi energy. Okay, so it is an on average energy of your system or your electronic material. This is the definition of Fermi energy in electronics. Okay, it has purely different meanings in statistical mechanics, and you can connect both the definitions, but that will take entire course in as such. But in intrinsic semiconductors, one very important property is that your Fermi energy is exactly in the middle of band. So your Fermi energy is nothing but Eg by 2, where Eg is nothing but band. So in intrinsic semiconductors, your Fermi level is exactly in the middle of band. It is at Eg by 2. Okay, these two things you have to remember. Then let's come to, and one more important thing. From valence band to conduction band, in between, you have no possible state. Your electron cannot be anywhere between this, or your hole cannot be anywhere between this. So no possible state is there between Vp and Cp. And always remember, Fermi energy is not an actual state. It's not like your electron can be at Fermi state. It's an average. Let's say you have 3 students who scored 10, 12, and 9. If you find the average of this, you will get some value like 11.5. If you get a value of 11.5, then this is your Fermi energy, but no student has actually got 11.5. Okay, so Fermi energy is not an actual energy level, it is just an average of that. Okay, so always remember, so there is no possible energy level between valence band and conduction band in intrinsic semiconductor. But if I go to the n-type semiconductor, then between valence band and conduction band, there is one more energy band, not energy band, energy level. So initially there was no energy level. In intrinsic, there is no energy level. But because of doping, because of the doping, between valence band and between conduction band, there is one more energy level, which is known as dopant energy level. And what does this dopant energy level tells you? This dopant energy level tells you, okay, if you want to make electrons free, so you know, right? So you have this phosphorus, silicon, 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 silicon. So your phosphorus made the 4 bonds, and this electron is free. But free means almost free, almost. It's not actually, it is completely free. It is almost free. If you give just a little push, it will get completely free. Okay. So this 5th electron is actually almost free, but not entirely free. So where he sitting at? This electron is sitting at its dopant level. This is the energy of this 5th electron. You get that idea? When you added phosphorus, there was 5th electron. And we said that that 5th electron is free. No, it is not completely free. It is almost free. You only need this much energy, very small energy. So if you give very small energy, this electron will go to the conduction band. It means it will get free. So it is almost free. So your dopant energy level is very close to the conduction band. So this is the energy of that 5th electron. So do you understand the idea, everyone? What is this dopant energy?
No, sir.
Okay. So you have the phosphorus, this phosphorus, and when we replace this silicon with phosphorus, so this phosphorus had 4 electrons. So 5 electrons, 4 of them made the bond, and 5th electron is here. Now we say that this 5th electron is free, but no, it's not completely free. It is almost free. Almost free. So let's say it is almost free. So what is the energy of this electron? ED. ED is the energy of this free electron. And in order to make this electron free, you need a very small energy. How small? Just this much. That's it. You only need this small energy. This much. That's it. And this 5th electron will get free, and then it will give you the conductivity. So this dopant energy level is nothing but the energy of the 5th electron of the phosphorus. Okay. And in order to make this electron free, you need a very small energy, and your electron will get free up. It will move to the conduction. Okay. Okay, fine, everyone?
Yes.
Everyone, is it clear?
So, sir, here can we say that the electron stays in that dopant energy level, not in valence band?
Yeah, by default, if you give the energy, then it will go to the conduction. No. Fifth electron sits in the dopant energy.
Yes, sir. So the fifth electron is living in the dopant energy level.
Yes, it is lying in the dopant energy. Fifth electron. Yes. Okay. Yeah.
Sir,
Yeah.
so why does this electron have less energy than the silicon? Like
No,
conduction band.
it does not have the less energy. So now you have two ways to make the free electrons. One way is that you can remove this electron. You can break the bond and you can remove this electron. Where are these electrons? These electrons are bonded, means these electrons are in valence band. So one way is you break the bond. So if you break the bond, you bring this electron from here to here. Okay. So what is second way? Second way is that you have the fifth electron. And where is that fifth electron sitting? That fifth electron is already almost free because this fifth electron is not bonded. Na? It's not bonded. So it's already free. So you need a very small energy to make it free. So that is why these electrons, bonded electrons are here. And this fifth electron is on this doping level. Is it clear?
Yes, sir.
So yeah, there are two ways. Either bring electron from here to here, which I said is breaking the bond, or because of the doping. So because of the doping means your electron goes from here to here. Fine. Everyone clear with that? So these things are not written in books, okay? I can guarantee you beforehand. Yeah. Now, any doubt? Okay. Then comes about the Fermi energy level. So you can clearly see that where is your Fermi level? So in N-type semiconductor, your Fermi level is very close to the conduction band. Very, very close to the conduction band. It is between dopant energy level and conduction, in between them. So Fermi level in N-type semiconductors is very close to the conduction. Okay. Now let's come to the P-type semiconductor. In P-type semiconductor, what will happen? There is again one more energy level. So in P-type semiconductor, there is energy level which is known as acceptor energy. Acceptor energy. So if you want to make holes, there are two ways in making holes. One is break the bond. So if you break the bond, so your electron is going from here to here and you get a hole here. But there is also hole making because of the doping. So you can make a hole very easily in your p-type. How? Because there is one additional free space available. Free space. This is an empty level available. So what you have to do is just shift your electron from here to here and you will get your hole here. So this level is coming because of the doping. So because of the doping, you have one free level very close to the conduction band, which is known as acceptor energy level, means it is ready to accept the electrons. And if you want to make holes, all you have to do is just bring the electrons from valence band to this acceptor level and you will get holes here. So once you bring electron from here to here, you get a holes here. So holes can be generated in two ways. Either bring it from here to here, which is bond breaking, and or use the doping. So doping means you will get one additional acceptor level. And once you get this additional acceptor level, what will happen? You can just bring your electrons from here to here and you will get holes here. So that is what happens in the p-type semiconductor. And in p-type semiconductor, your Fermi energy level is very close to the valence band. Valence band. So if I ask you this question, and 95% of the students get this wrong, and that question is there any physical energy level present between inside the energy gap in case of extrinsic semiconductor? Is there any actual physical energy level present in the band gap for the case of extrinsic semiconductor? Yes or no?
No.
No. Okay. Anyone else? Yes or no?
Yes.
Yes, sir.
Yes.
Answer is yes.
Nah.
Yes.
In case of intrinsic, there is nothing present. But in case of extrinsic,
Sir,
ED and EA is present.
sir,
Hmm?
सर वो मैंने EA और VB के बीच में सोचा कि वहां पे
नहीं,
एक्सचेंज
No. In this entire thing, EA and ED is present, right? So you can clearly see because of the doping, there are additional energy levels coming inside the band. So that you have to keep in mind. Usually students think that no energy level can exist in band gap, which is true. But in case of extrinsic levels, two energy levels actually come. One in case of N and one in case of P. Okay. Okay. With this idea said, I am almost about to end. Now, what is known as density of states? So all the students in my course, we have derived this formula in quantum statistics. I hope you have watched this lecture. And if you have watched this lecture, what is density of states? You have this band gap. So let's say this is a band gap, and this band gap is going from 2 electron volt to 4 electron volt. And let's say this band gap has 100 states, means 1, 2, 3, 4, 5, 6. Then what will be the density of states? Number of states per unit energy. So how many states are there? 100. How much is the energy? 2. So density of states will be 50. So density of states is nothing but number of states per unit energy range is known as density of states. So you will have density of states in conduction band, and you will also have density of states in valence band. You have to remember the direct formula. If you do not remember the proof, even if you remember the proof, this formula is so important because it is going to be used in 3 places: statistical mechanics, electronics, and what do you say, solid state. So this formula is very important to you. And the density of states formula says 2 into 2 by me kt by h cut square. But the most important thing to remember here is that your density of states depend upon mass into temperature 3 by 2. Even if you remember this much, that will be very important. That your density of space depends directly on mass raised to power 3 by 2 and temperature power 3. So now what is the mass here? This is known as the effective mass of the electron. Now I am coming to the effective mass. The mass of electron when it is completely free, and mass of the electron when it is bonded is two different things. Why it is two different things? Because of the wave nature of the electrons. Electrons can actually go around and interact with other electrons, and not the entire electron is free to participate as such. Because now you have to think of it, electron as a wave. Because of the wave nature, or you can just imagine this, the effect of the electron inside the material. So mass of the electron is not m completely, it is the effective mass of electron. So your mass inside the solids, sometimes it increases, sometimes it decreases. So you cannot say in every case that mass of electron is exactly equals to 9.1. That is the mass of the free electron. But the mass of the bonded electron is not this. Mass of the bonded electron is known as the effective mass of electron. And this mass is changing because of the wave nature of the electron. So in your conduction band density of states, the mass is for the mass of electrons. Similarly, for valence band states, the same formula, only thing that is changing is instead of mass of electrons, you have mass of holes. So now you have mass of holes, which means effective mass of holes. That how much your holes are carrying the mass, how easily they can move around. What is the inertia of your holes? Mass of the holes means what is the inertia? Inertia tells you the mass. So with how easily your hole can move from one place, that will actually give you the what is an effective mass of the hole. And why the effective masses are coming? Because of the quantum nature. Okay. And how we can calculate this effective mass? The formula for effective mass is this. You will be given some dispersion relation. For example, energy is equals to alpha k square. Dispersion relation is a relation between energy and k. I have discussed this in the lecture of quantum statistics. You can watch that lecture. So dispersion relation. And if the dispersion relation is given, using this dispersion relation, you can find the mass of the electron or mass of the proton using this formula, where h cut square. In this case, if I find d square e by dq square, so I have to differentiate it double times. So it will get 2 alpha. So your effective mass will come out to be h cut square by 2 alpha. This will be your effective mass. That's it. That's a simple equation. Okay. If you will be given with the dispersion relation, and then you have to find the mass. The last two formulas that we need is how many number of electrons per unit volume are there in conduction band. That formula is given by NC. What is NC? NC is the density of states in the conduction band, equal into exponential minus EC, energy of conduction band, minus EF, Fermi energy, divided by KT. And P is what? NV minus EF minus EV by KT. These are the two formulas. This tells you number of electrons in conduction band, and it tells you number of holes in valence band. And for both the formulas are in terms of NC and NV. NC or NV are nothing but density of states in conduction band and density of states in valence band. Okay. Okay. There was one more formula which I had to give you. Where is that formula? Fermi energy formula. I wrote it somewhere. Fermi energy formula. Where that went? One more formula was there. Fermi energy formula. I written it in somewhere. Yeah, this is. Okay. Very important. What is Fermi energy formula? For so what I told you, for intrinsic semiconductors, your Fermi energy is nothing but Eg by 2. When I was saying this, I assumed that density of states in conduction band and density of states in valence band are same. If this condition is satisfied, then you can clearly see you will get ln1 and this thing will become 0. So if this thing becomes 0, then your EF is actually equals to Eg by 2. So let's say you have intrinsic semiconductor and you have one conduction band, while you have one valence band. And in this case, if number of density of states in conduction and density of states in valence are same, then your energy band gap will be completely in center. But let's say the density of states here and here are different, then you have to use this formula. And this formula suggests you that EF equals to Eg by 2 minus KT ln NC by NP. Then your band, then your Fermi level is not exactly in the center. And can anyone guess that why the density of states can be different in both? Why density of states can be different? Because your density of states depend upon the mass. So your conduction density of states depend upon the effective mass of electron, and your valence density of states depends upon mass of holes. So if the effective mass of electron and effective mass of hole is different, in that case, your density of states will also be different. And if your density of states are different in conduction band and different in valence band, in that case, your band, your Fermi level will not be in the middle. It will either be up or it will either be little. Okay. Any doubts? And everything clear to you. Fine. There are 14 formulas that you need in this chapter. All of them are summarized together. Nothing beyond this you need in semiconductor physics. Nothing beyond. It's an extent of whatever you need for your electronic semiconductor physics. If anyone has any doubt, please ask me and tell me if you are clear with that. I will go with the questions.
Sir?
Yeah.
Sir, in P-type semiconductor, we saw there's an acceptor level. So more electrons from valence band will go to acceptor level than to conduction band.
Yes.
That 100%. Is the favorable probability.
Yeah, not probability. It happens. If 10⁻6 electrons are going to acceptor, then only let's say 10⁻2 will go to the conduction.
Okay. And same thing happens in N-type.
Yes, that is why I told number of holes is approximately equals to doping holes. I ignored that any of them is going above because that number is very small. Right? You have got it right.
Okay.
Okay, let's come to the first question. So first question, yeah, please.
सर ये क्वेश्चन है सर, ये इफेक्टिव मास सर होल्स का मास मतलब क्या है सर?
Holes does not have mass. Holes means that how fast this electron can move from one position. So let's say I am sitting on a bench. So I am on one side of the bench and other two seats are empty. So if I go from, so this I am sitting here and two seats are empty. If I decide, okay, let's go and sit here. So if I'm moving here, then vacant space is here and now I am here. And so in a way, you can think in two ways. One way is that electron moved from here to here. Or you can even imagine that, no, electron did not move. Your hole moved from here to here. Your hole moved from here to here. So how easily your hole is able to move? In reality, electron is moving. But you can imagine it in the way that, no, electron is not moving. Your hole is moving or your vacant space is moving. Initially, vacant space was here. Now the vacant space is here. So your vacant space move from here to here. And how easily he can do that? That will tell you the inertia, or yeah, that will tell you the mass of the. Okay. That's completely a mathematical idea. There is no physical mass of the. Okay. It's a mathematical concept. Physical mass of the whole cannot be defined. You cannot find a particle known as whole. Okay. Good.
Okay.
Sir,
Yeah.
hole is nothing but the vacant space left after the electron has moved from that side. So how can that vacant space have some mass, sir?
No, it does not have any physical mass. You are assuming it to be have a mass. It's a mathematical mass. Okay. You are assuming that how easily it can move. So you are telling what is its inertia, and from inertia you are giving the mass. Okay. So the example I gave you, if electron goes from here, it was an empty space. It has no mass, nothing. So electron goes from here to, and it means whole is here. So in a way you can think that no, whole goes from here to. So how easily this whole can move? That will tell you the inertia, and from inertia you will get the idea of mass. You are getting the idea of mass, equivalency of mass, not exactly the mass. You understand? There's a difference between them. It's an equivalency of mass. You can because not every time I can imagine that okay, electron is going, hole is going. So what I did is that okay, let's bring a model in which I am assuming hole as a particle, and if I am assuming hole is a particle, then I have to give it some mass, and that is why I'm giving it a mass. So from where that mass will come, that how easily it can move, so I will get inertia. So from inertia, I'm giving it some value of mass. Okay. I hope it is clear. Now let's come to the question. The question says that. Yeah. Yeah. So in intrinsic semiconductor. So
Bhaiya, shouldn't be the.
Yeah. Yeah. Tell me. Hello.
Yeah, hello.
Yeah. Tell me.
Hello.
Yeah.
Bhaiya, shouldn't be the electrons and holes should be always same because both effect are.
They are effectively not same. Not always. They are not same. Not effectively same. So this is a very simple image I am presenting you. The electron moved and hole produced. In reality, there is a time delay between electron moving and vacancy being generated. Inside atoms, there is a little time delay between how fast the electrons move from one place to another. So when your bond break, your atom needs some time to again make a bond. So there is a delay, small delay. Electron moved first, and then your atom needs some time to again make a bond. So there is a time delay between the generation of hole and generation of electron. So the effective mass of both cannot be exactly same. It's not a physical thing. It's not actually what is happening in classical mechanics. If I move from this position to this position, immediately this seat is not getting vacant. Your atom needs some small time to be ready to make the bond again. And that time delay actually is responsible for different masses of electrons and holes. You getting my point?
Yes.
You can imagine that an atom needs some time to again make a bond. So that is the condition. Okay, good. Now let's come to yeah.
Sir, you said is this a constant quantity? Me and Mn?
No, absolutely not. Absolutely not. So let's say your valence band looks something like this. So you can clearly see the slopes are changing at different points. So d square E by dk square can change at different points. So at different energy levels, your effective mass can also be different.
Okay, thank you.
Okay, so now we have an intrinsic semiconductor, and free carrier density is given to you as a function of temperature. And they are asking you what they are asking you. They are asking you the band gap. So in intrinsic semiconductor, I know that what kind of charge carrier density I have, which is Ni. And the formula for Ni I studied is Ni equals to N naught e raised to power minus Eg by 2 kBT. So I will just bring this formula out, and then I have this formula. This is Ni. Now if I take log on both sides, I will get log N, and I will get log N naught and minus of Eg by 2 kBT. Now let's bring it here and let's write this thing like ln n minus Eg by 2k y 1t ln n dot. Now let's multiply divide by 1000. Why I did this, I will tell. I multiply divide with 1000. So I get ln n 1000 by t minus Eg by 2000 k plus n dot. Now my graph, you can clearly see it is between ln n and 1000 by t. ln n and 1000 by t. So this thing is y and this thing is x. So I can write y, x, and this is slope plus c. So what is my slope here? My slope is nothing but equals to minus Eg by 2000 k. And from the graph also you can find the slope. How you can find the slope? So you can clearly see slope is nothing but y2 minus y1 by x2 minus x1. So this is my y2. Value of y2 is 32.5. This is my y1. It is nothing but 36.5. What is my x2? x2 is 3 and x1 is 2. So 3 minus 1, 2. So my slope also comes out to be minus 4. And my slope is also minus Eg by 2000 k. So from there, I can actually say that my Eg will be 4000. So it is 10 to the power 3, 4000 kBT. Okay. Oh, sorry, 8000 kBT. Yeah, 4 into 2. Yeah, 8000 kBT. So then I put my value of kb and I get my value of Eg as 0.69. So clear, everyone? So which formula we used? This one.
Sir,
Did
what
you got-
value of kb we
It was
have put
given.
here?
It is given. I just use this.
Okay.
Yeah. kb will always be given. You can just go without remembering. Yeah. Okay. Second question. Consider a doped semiconductor. Now we are not in n-type semiconductor. We are now in, we are not in intrinsic. Now we are in extrinsic. Electron mobility is given. Hole mobility is given. And intrinsic carrier density is also given. And they are saying that what is the hole concentration so that your conductivity is minimum. So conductivity is minimum. So what is the formula for conductivity in intrinsic semiconductors? The formula we studied, N E nu n, number of electrons per unit volume. E nu n is the mobility of electrons plus number of holes. E nu p, mobility of the holes. Then I use this formula where NP equals to Ni square because I need to find the number of holes. So I also have to write N in terms of P so that my entire equation in terms of P. That is what I want because I want to minimize my conductivity. So what should be my value of P so that my sigma is minimum? So in order to find that, first thing I have to do is write the entire equation in P. So in order to do that, I will use the equation I will say that N into P is nothing but Ni square. This is my law of mass action. So from there, your N will come out to be Ni square by P. So I put my N as Ni square by P, nu N, P, nu P, E I have taken common and written. So now you want to minimize your sigma with respect to P. So whenever you have to find the minima, what you do? You do D curly sigma by curly P as 0. This is what we do to find maximum minima. And if I do this, so I will derivate this, I will get minus Ni square by P square nu N, and its differentiation will be just simply nu P. So from there, you can easily see my P square will come out to be Ni square into nu N by nu P, or my P will come out to be Ni by Ni into under root of nu N by nu P. Is it clear all?
सर
Yeah.
सर वो ऊपर सब्स्टिट्यूशन क्यों किया वो एक बार समझना है.
Because first of all, you want to minimize this with P. So you have to first write the entire equation in P. So first write your N in terms of P so that your entire equation is now in P, and now you have only one variable because right now your N is also variable, P is also variable. So first bring entire equation in P and then start minimizing the sigma with P. Okay. So just to write entire equation in P, I did that.
Thank you so much, sir.
Okay. Now, this is the most important question. This I have not covered in the theory as such, and this is what you have to see. Now you have PN junction. PN junction means you have P-type semiconductor, you have N. I will be covering P and diode separately, but just to do the Fermi energy level, I am doing this. So you have P-type semiconductor, you have N-type semiconductor, and you combine that. How will the energy diagram will look like? how will your band diagram will look like? And no person actually knows this very well. I had a very huge confusion while I was preparing for exam. In PhD, my confusion got cleared. So let me explain you how. So I have not combined. So let's look at them separately. I have P-type material, I have N-type material. So I have bucket 1, I have bucket 2. So in my bucket, in this, the water is only till here, right? Because my Fermi energy level in P-type is close to the valence band. So in this bucket, my water is only till here. And in this case, my water is till. So because in N-type, the Fermi energy level is till close to the conduction. Now I have two buckets and now I am connected. So what do you say? Till what point the water will flow between? Till the Fermi energy of both the levels will become equal. Do you agree with this? So water will flow or electrons will transport until the Fermi energy in both the materials become equal. Or you can think that water in both the buckets is equal. So let's do. So if I combine that, you will see that now the Fermi energy is same. Throughout the material, Fermi energy is balanced. Fermi energy is balanced. But what will happen? What will happen as such? You can think that water in this case will come down. So this bucket was at higher water and this bucket was at lower water. So water in this case will come down, and little bit water in this case will go up. It means bands are bending. Means these bands are going down. These bands are going down. So you can clearly see that these bands, so initially bands were here. So these bands bent little bit up and these bands bent little bit down. So you get the bands like this. So these bands bend down. So you can clearly see the diagram in which bands are bending so that this Fermi level and this Fermi level comes together. So these bands actually bend down. So this is known as band bending. And this is the how you get a diagram. Is it clear till here? I have not applied any battery. It is just a simple diagram. So one bucket, second bucket, in order to maintain the water same. So water in this has to come down. So the all entire bands in this will come down. So if it come down, your diagram will look down something like this. Initially they had like this, but now this came down. So this will be like this. Okay. Fine, everyone?
Yes, sir.
Okay. Now there is very important thing I want to say. Let's say I applied no battery. No battery at all. I am applying no battery. In the absence of battery, holes move up the hill by themselves. If I'm applying no battery and if I'm in a hole, without requirement, without any need of any external help, I can move up. So electrons from N can move up. So can you tell me that electrons in N are majority or minority?
Majority.
Minority. In N, oh sorry, number of holes in N are minority or majority?
Minority.
So minorities are moving by themselves. I'm not applying any battery. So by default, hole has a property that it can move up the hill. So it is moving up the hill. So holes are moving by default. And electrons has the property to go down the hill. So in P, there will be some electrons. Some electrons will be there. Very few minority holes are there. So they will move by default below. So they will move automatically below and holes will move automatically above. So minority charge carriers are moving automatically because electron can move, hole can move up. So it is holes from here are moving up. Hole cannot move down automatically. P has many holes, but holes cannot move down by itself. That is why no hole is coming from here to here. But holes can move up automatically. That is why whatever thode bahut holes it has, it is going up. Similarly, by itself, electrons can go down. That is why all the electrons in P are going down. Now, N has so many electrons, but automatically electron cannot go up. That is why no electron from here is going up. So by default, minority charge carriers move. But to move the majority charge carriers, we need to apply the battery. Okay. So under no biasing, I am not biasing. Biasing means I am not applying any battery. So if I'm applying no battery, this is my Fermi band. Now let's apply the battery. If I apply the battery, what will happen to this barrier? You can see this barrier is there. If electron wants to go from here to here, it has this barrier. So you know that if I do the forward biasing means helping the electrons. If I do the forward biasing, this barrier will reduce, will get smaller. And if I do the reverse biasing, this barrier will increase. So under biasing, how your diagram will look like? You can clearly see. Now your Fermi energy levels are not same. In biasing, your Fermi energy levels will not be same because now you have biased it. It's not a natural process. So now your Fermi levels are not same. Now what will happen? It will definitely happen that now in forward biasing, your barrier will reduce. So this barrier got smaller. So what happened? This N moved up, little bit up, so that this barrier reduces. So this was an initial barrier, so this moved up. So now this Fermi is up and this Fermi is down. In case of reverse biasing, your barrier increased. Reverse biasing means I'm not helping electrons, I am repelling electrons. So barrier increase. Barrier increase means initially this was a barrier, now it is even more. It is even more. So this is what happens. So if this is even more, then this will be the situation. Okay, this will be the situation. So initially it was like this, and now you applied the reverse biasing. So this barrier will increase. So initially Fermi levels were like this. So now Fermi levels are like this. So barrier increased. So this is your energy band diagrams for forward biasing and reverse biasing. And they have asked in the problem that what will be the diagram for forward. So the diagram for forward, you can clearly see will be option number A. You can clearly see that matches. You can clearly see the option number A is matching. Okay, ye samajh aaya? This is clear, everyone. Very important.
Can you see the options?
Yes, sir.
Yeah, you can see the options. In this, you can see the band Fermi is same. So Fermi is same only in the absence of biasing. But in this, they are asking for biasing. For forward bias, they are asking. So this option is definitely wrong. In this, you can clearly see this is up, this is below. But you can clearly see we saw that for forward biasing, this has to be up and this has to be down. Because initially this was the Fermi level and our barrier reduced. So this went up. So this went up. So only option number A is matching up. Okay. And this is for the reverse. This diagram is for the reverse. This is for forward. This is for reverse. And this is for intrinsic. Oh, sorry, no bias. Okay. Let's see another similar question. Now you have NPN transistor. You have N, then P, then again. So now let's see how it will look like. So N has the Fermi level towards the conduction band. P has the energy level lower to the valence band, and N has again close to the. Now I want, when I connect them, what will happen? Fermi energy level will become same. So in order to make the Fermi energy level same, do you agree that this has to come down, this has to go up, and this has to come down? So you have 3 buckets of water. Sir. So this will happen. So this both will, day and day will come down, and this will go up. And which diagram is that? This went down, and this went up. So which diagram is that? This is the diagram, which is option number B. So now you can just looking at the diagram, you can figure out how to solve the question. Clear, everyone? Concept behind that? How I solve this?
Yes.
Okay. Okay. The last problem of the today. So you have a PN junction diode. Okay. So something is given and rho is given to you. Rho is given. Means
Sir?
start. Yeah.
Sir, again, in the last question, if we apply the biasing, the same concept will be applied, no? Which we had discussed in the last question.
Yes, yes. Then this, so one of them, so you identify that it is either reverse or forward. So do this thing and try to see if this is reverse or forward.
Okay, sir.
Now there will be 2 reverse and 2 forward, right? You know, na?
Yes.
One will be this junction and one will be this junction. So think if this junction is forward or this is forward, or which one is forward, which is reverse. Okay. So you will get a good insight. So now the rho is given to you inside. So PN junction diode, I will come to you, but from basic diagram, you can clearly see that rho is given to you. And if rho is given to you and they're asking that what will be the electric charge density is given, electric field is asked, you do not need any knowledge of electronics, you need Gauss law. Gauss law is what? Del dot E equals to rho by epsilon naught, and electric field is asked in respect to x, so I'm only taking x component. So del dot E can be written as curly E by curly x equals to rho by epsilon naught. Now rho is a straight line, so rho can be written as rho equals to rho naught into x, y equals to mx, right? Because there is no intercept is 0. So that is why y equals to mx, or you can say rho equals to rho naught x, or rho equals to alpha x, anything you can write. So rho is alpha x. So now what I will do, dE by dx equals to rho by epsilon naught, value of rho is alpha x. So now what I will do, I will keep dE on this side, dx on the other side, and then I will simply integrate on both sides. This I will get as electric field, and x integration is x squared. So your electric field is vary as x squared. So which graph it will be out of 4? If your electric field vary as x squared, it will be parabol, which is option number D. Okay. Now there is a homework for you, and that homework is, one is this question, and I'm using the same formula as question number 1. Whatever I did in question number 1, you have to do the same thing in here and solve this problem. And then these are the 2 homework problems for those students who are not the part of my course. So if you're not the part of the course and still wants homework, then try these 2 problems. For the students who are already the part of my course, your homework is complete the GATE PYQ quiz. Now you are able to do that. Go to the GATE PYQ quiz and you will see there is a quiz on semiconductor physics. Give that quiz and give that in the morning after reading the notes nicely, and then see how much you are scoring. Okay, and go with the formula revised. Do not look at the formula. Remember the formula and then give the quiz. Okay, so let me stop recording. It will be very long class.